Hey everybody. So on Friday we started talking about the basics of the atom. And remember here we said that atoms are made up of three subatomic particles, those being protons, neutrons, and electrons. And remember we said protons are positive, they're in the nucleus, they had a mass of about 1 AMU. Neutrons were neutral, but in the nucleus, and they also had a mass of about 1 AMU. And then we had these electrons, which were the negative charges in an atom. They were outside the nucleus, and they had a mass of 0 AMU just because they're about 1,000 times smaller than protons and neutrons, which are already incredibly small. And so then we started talking about some of these other things like the atomic number, which remember is the number of protons that an atom has. And remember, this is what identifies the element because all atoms of the same element end up having the same number of protons. And then we also mentioned the fact that protons and electrons are pretty much always equal to each other in an atom, which means that they're generally electrically neutral. And so then this led to this idea of, okay, well, what's going on in terms of the mass? And so most of the mass of an atom comes from the nucleus, which remember is the number of protons and neutrons that are located in the nucleus. And this is what accounts for what we call the mass number, which is the total number of the protons and neutrons that are located in the nucleus. And so with this led to this other idea about atoms of the same kind that ended up having different masses. For example, you guys have heard of a couple like carbon 12 versus carbon 14. And hopefully you guys remember from biology, carbon 14 is something that's used in carbon dating because it's radioactive. And so these are what we call isotopes. And so remember, isotopes are atoms of the same element, meaning they have the same number of protons, but they have different masses, which means that they have different numbers of neutrons. And so this is pretty much where we left off. And so we have oxygen always has 8 protons, but it can have a mass number of 16, 17, or 18. And so what accounts for the differences between the atomic masses of oxygen? And I know a bunch of you guys are already saying it in your heads, it comes down to the number of neutrons. And so we got this nifty little table here. And so we have our isotopes, oxygen 16, 17, and 18. Now remember, since they're all oxygen, they all have to have the same number of protons because that's what identifies the element as oxygen. And so when we look at the periodic table, the atomic number happens to be 8, which remember means that there's 8 protons. And so now let's look at figuring out the number of neutrons. Now remember, whenever it says dash 16, dash 17, or dash 18, all 3 of these represent the mass of that isotope or of that atom. And so oxygen 16, which has 8 protons, has to have a total of 8 neutrons in order to get the mass of 16. Whereas oxygen 17, having 8 protons, needs 9 neutrons, and oxygen 18 needs 10 neutrons in order to get the mass number of 18. And so one of the nice things is that we can write the atomic number and atomic mass along with the element symbol. And so this is what we call isotopic notation. Now, isotopic notation always has this kind of standard format as we'll just use element X here. And it's always the mass number on top and then the atomic number below it. Now, we're not going to talk about this today, but later on we'll talk about this idea with it. And just for fun, the charge always goes in the top right side. Now, for these, since we're just talking about isotopes, nothing to do with charge yet, we can essentially eliminate the charge as part of what we need to write. And so if we're writing out oxygen 16, we're going to write it out as oxygen as our element symbol. And then remember, the mass needs to go on the top left side, and then the atomic number needs to go on the bottom right side. So this is how we write the isotope for oxygen 16. Then if we're writing out oxygen 17, it's oxygen 17 with an atomic number of 8. And oxygen 18, we got the mass on top and the atomic number below it. And so this is how we can write or show our different isotopes using kind of a standard format. And so our next question is, how would you represent lithium-7 using its atomic symbol? And so lithium is Li, and then remember when it says -7, that represents the mass. So 7 is going to go on top. Now when we look at the periodic table to figure out what the atomic number of lithium is, we can then write that on the bottom left side. And so as you're looking at your periodic table, you should notice that the atomic number for lithium is 3. And so we can write that just below our 7 there as our atomic number. And so this is, remember, what we call isotopic notation. And so this is how we show the different isotopes that exist for various atoms or various elements. And so this brings up this idea of atomic mass units. Now, atomic mass unit, or AMU, is something that we briefly discussed on Friday. And so atoms overall have this really, really small mass. For example, a mass of a copper atom is 1.0522 times 10 to the negative 22nd grams. And remember, that's just an average because it includes all of the different isotopes of copper, not just one isotope. And so what that means is one copper atom is equal to 1.0522 times 10 to the negative 22nd grams. Now, for those of you paying attention, you probably caught on. This looks a whole lot like a conversion factor, which means factor labeling is soon to follow. And so our question is, pennies, which are made up of mostly copper, and that's true of definitely old pennies. It says that one penny has a mass of 3.1276 grams, and how many copper atoms are there in a single penny? Now, as we're starting off, do you think this is a big number or a little number? Hopefully you said a big number, because remember, one copper atom is really, really tiny in terms of the mass, especially compared to the overall mass of a penny. And so we're going to start by saying 3.1276 grams of copper. Now notice for this, we wrote both the grams as well as the element we're kind of in question or that we're talking about. And so as we start our factor labeling, since remember we're talking about the number of atoms, we're going to put one atom of, we're going to do one atom of copper on top over our 1.0522 times 10 to the negative 22nd grams. Now, when we start multiplying this out, we end up getting 2.9724 times 10 to the 22nd atoms of copper. And so notice that is a huge, huge number of atoms, which makes sense because remember, atoms overall are incredibly tiny. And so this really does help indicate just how small atoms are overall. And so that usually means that they're encountered in really, really big numbers. And so generally, because atoms are so light, kilograms and grams are not exactly the best for measuring their unit of masses. And so the special unit of AMU, or atomic mass unit, was developed. And so one AMU, or one atomic mass unit, is equal to 1.6605402 times 10 to the negative 24th grams. Now, just so you guys know, you don't need to memorize this. Notice it says do not memorize, which means that on tests and quizzes, I'll always give you guys this number. It's just something that you need to understand how to use. And so let's talk about where this number actually comes from.